Now I want to take the next step in talking about derivatives for multivariable functions. We're going to talk about the directional derivative and the gradient. So where are we starting from? Previously, we've seen how to find the partial derivative df dx, which is the derivative of f of xy in the x direction as y is constant, and the partial derivative df dy, which is the derivative of the function in the y direction as x is constant. So now we're going to find the derivative of f of xy in any direction. So as we do this, we're also going to find the formula for a very special vector, which has these two properties. Now remember what determines a vector: its magnitude and direction. So for this vector, at every point, its direction will be that it points in the direction of the largest rate, and its magnitude will be that largest rate. So I want to get into this topic first by talking about a little application. So there was an example I talked about before, which was measuring the ocean surface temperature. And let's say we had the temperature changes 0.1 degrees per meter to the east and negative 0.2 degrees per meter to the north. Then let's say swim and we look at the temperature at a new spot, which is 15 meters east and 20 meters north. Okay, so let's think of 15, 20 as the vector of our displacement. Before we start, where we finish. So as we saw previously, this is going to result in a total change in temperature, again assuming these rates are constant, of 0.1 times 15 plus negative 0.2 times 20. So put that together and you get negative 2.5 degrees. Okay, so there is your delta F, or your approximate delta F, or your delta L, assuming the rates are constant. Okay, now let's ask an additional question. That's the total change. What is the rate of change? So rate of change we know should be degrees per meter. So what does that mean we need to do? We need to calculate how many meters were traveled as the temperature changed. So that's just going to be the length of the vector. So the displacement vector was 15, 20. So the magnitude of that is going to be 25 meters. So our rate of change over that little trip is going to be negative 2.5 degrees divided by 25 meters. So that just works out to negative 0.1 degrees per meter for that specific trip. Okay. So there's the application, and so where we're headed, the challenge is going to be to come up with a general formula for the rate of change at a given point in the direction of the vector r, s, where, say, we know the two partial derivatives at that point. Okay. So that's one way to think about it in terms of application. I also want to take a moment to try to think about this geometrically. So geometrically, what's going on? Well, previously, we saw that we could describe the partial derivatives geometrically by drawing a trace. So on your surface, you could draw a trace, either a trace in the x direction or a trace in the y direction. And then you could find the slope of the trace at that point. So alternately, you could look at the tangent plane and then draw a trace of the tangent plane in the x direction or the y direction. Now, we focused on sort of the x direction where y is constant and the y direction where x is constant. But there's no reason to only consider those two specific traces. Starting at a point and to draw a line either along the surface or along the tangent plane, how many ones can you draw? How many directions can you head in? Infinitely many directions. So that's going to be our task. Our task is going to be to take a look at the graph for a second, a graphical representation. So that's going to be our graph. So we can, from our given point, which is marked off there with the black dot, we've got our surface and then also a tangent plane on it. we can head off in any direction, and we're going to want to find the rate of change for that thing. So geometrically, that's what's going on. And here's a little bit of a technical explanation of how we might label things. We're not going to need that for our actual calculation, but you can take a look at that. So next, we're going to develop the formula. So let's say we've got the function f of xy, and we're starting at the point P, which is a comma b, and we're going to head off, head off in the direction indicated by the vector v, which I'm going to call r comma s. So as we displace along v, so first of all, we know that we're going to move r units in the x direction and s units in the y direction. But we know those rates. The rate of change in the x direction is just df dx, and the rate of change in the y direction is df dy. So therefore, moving r units in the x direction is going to produce r times df dx units of change, and moving s units in the y direction is going to produce s times df dy units of change. So our total change is r times df dx plus s times df dy. But as we just saw in our contextual example, that's the total change, that's not the rate. So if v is not a unit vector, then really it's that much change per magnitude of v units. So the rate of change, we need to divide by that and put it all together, and we get the rate of change in the v direction is r times f sub x plus s times f sub y divided by the magnitude of v. So that is the rate of change in that direction. Now we can go one step further to simplify this. What if v was a unit vector? If v is a unit vector, then we're just dividing by 1. Which is the equivalent of doing nothing. So if we have a unit vector, then the rate of change is just going to be r times f sub x plus plus s times f sub y. Okay. So now let's introduce this formally. So the derivative of the function f in the direction of the vector v is what we call a directional derivative, and the notation for that is big D sub v of f. And an alternate notation would be, as suggested by partial derivative notation, partial df dv. And again, remember that v is a vector. Okay. So we are generally going to, because the formula is simpler when we use unit vectors, we're going to try to stick with unit vectors. Although we don't necessarily always have it, we can always take a vector and reduce it to a unit vector for taking partial directional derivative. Okay, now, next up, we're going to introduce some notation for what's going to be a very, very, very important concept for us. And it's actually going to simplify this expression tremendously. So, the formula for the directional derivative is r times f sub x plus s times f sub y. What type of thing does that, what type of calculation does that remind you of? Well, here's a hint. It's something times something plus something times something. So this expression can be written as a dot product. And the question is, a dot product of what? So you'll notice that one of the things we'd be taking the dot product of is going to have the two partial derivatives in it. So that's going to be a special vector. So for the function f of x comma y, its gradient vector is df dx comma df dy. And the notation for this is this upside down triangle of f, and that's a vector, so we put an arrow over the triangle. That triangle is called nabla. We can just read this as it's the gradient of f, which we'll just say grad f. And again, remember that f, it's a scalar function, but when we take the gradient of it, it produces this vector. So grad f is a vector. We're going to be using grad f a lot. It is a very, very important concept in multivariable calculus. So put it all together, we notice that the directional derivative can be written as this dot product. So if v is not a unit vector, we can write the directional derivative as grad f dot vector v divided by the magnitude of v. But of course, if it's just a unit vector, it reduces in a nice way. So the directional derivative of the function f in the direction of vector unit vector u is just grad f dot u. So we showed how the formula makes sense, but then we also introduced this new concept and this new notation for the directional derivative and the gradient. So now let's apply this to a problem. Okay. So for this function, f of xy equals 3x cubed plus 5y squared with vector v equals negative 2 comma 5. Find the directional derivative d sub v of f at the point 2 comma 3. So let's do it. So what do we need? Well, we know we're going to need to take a dot product of the gradient of f, and we're going to get used to using the unit vector. So we need both of these things. So first of all, what is the gradient? So we need the partial derivatives, df dx and df dy. So df dx is just 9x squared. Df dy is just 10y. So that tells us that the gradient of f is 9x squared, 10y, and I'm going to write it as a column vector. Now, we also are interested in what's happening specifically at the point 2 comma 3. So, gradient of f at the point 2 comma 3 equals, so plug it in, and we just get 36, 30. Okay, so there's our gradient at the point. So now we also need a unit vector. So our unit vector, u, is just going to be v over the magnitude of v. So magnitude of v, let me pull that out. So you can see for negative 2 comma 5, that's just going to be 2 squared plus 5 squared is 29. So 1 over rad 29 times the original vector, which was negative 2, 5. So put that all together. I like to write it as one vector. Negative 2 over rad 29, 5 over rad 29. And now we can find the directional derivative. We've got the pieces. So dvf equals, we can now use just the unit vector. So that's going to be 36. And this is the directional derivative at our point. 36, 30 dot negative 2 over rad 29, 5 over rad 29. So combine and calculate, and you get 78 over rad 29 and if you want an approximation of that, that's about 14.5. Okay. Clean that up. There you go. Okay, so there's your basic calculation of a directional derivative. Let's do another problem. Okay. So for this function, f equals y squared over x. Let's find the directional derivative, big D sub v of f, for the vector 3, 4 at the point 3, 2. Okay. So first off, we're going to need the gradient of f. So gradient of f equals, so first we need df dx. So I'm thinking of this as x, for the function as x to the negative 1 y squared. So the derivative is just going to be negative x to the negative 2 y squared. And then df dy is just going to be 2y over x. Okay. And next we need the gradient of f specifically at our point, which was 32. So that's going to be negative 3 to the negative 2 times 2 squared in the first component, and then 2 times 2 over 3 in the second component. Work it all out, and you get negative 4/9, 4/3. So at our point, that's the gradient vector. Next, we need the unit vector. I like to find that first. The unit vector is just going to be v, and then we're going to divide by its magnitude. So the magnitude of v, it's 3, 4. So 3 squared plus 4 squared is just 25. So this is just 1/5 times the original vector. And of course, that just simplifies to 3/5, 4/5. So there's a unit vector. Now we've got all that down, we can very easily write the directional derivative. So directional derivative for v, in the direction of v of the function f is just the unit vector, oops, no negative there, or rather negative, but the other way around, negative 4/9, 4/3, dot 3/5, 4/5. Okay. So combining and calculating, so that's going to be 36 over 45. You can reduce that to 4 over 5, or if you like it as a decimal, 0.8. Okay. So we now know how to find the directional derivative, and in the process, we defined a vector called the gradient vector. Now we specifically talked about gradient vector if it's a function of two variables. So I just want to mention that we can define the gradient for functions of 3 or more variables. So if you have a function f of x, y, z, the gradient of f is just f sub x, comma f sub y, comma f sub z. And if you have 10 variables, you would define the gradient in a similar way.